Imagine the Grand Line, a sea so chaotic and unpredictable that even the best navigators struggle to survive. To conquer these waters, you don't just need a log pose, you need to understand the underlying laws of motion. In our world, these are the Navier Stokes equations. Before we find the One Piece, we must understand our pirate crew, the fluid particles. Instead of tracking every drop, we look at a representative volume. First rule, pirates are never created or destroyed, they just move. This is the conservation of mass. If the water is incompressible, packed tight like a crowd, the amount entering must equal the amount leaving. Rule number 2, Newton's second law. For a fluid, we say, density times acceleration equals the sum of all forces. But acceleration in a fluid is tricky. Imagine Luffy running on the deck of a moving ship. We call this the material derivative. It has two parts, the local change in time and the convective change from moving to a new spot. The convective term is why fluid math is so hard. It's nonlinear. It's like a wave that creates its own wind. Now the forces. There are three main ones: pressure, gravity, and viscosity. Pressure pushes from high to low intensity. In math, this is the negative gradient of pressure. Gravity is the weight of the world, pulling everything down. We represent this as rho g. Finally, viscosity. Think of this as the friction of the sea. Viscosity smooths out the differences in speed. Let's assemble the master equation. Density times acceleration equals pressure plus gravity plus viscous forces. To make it easy to scale across different seas, we use the Reynolds number. If rho is very high, like a storm, viscosity is negligible. If rho is low, like syrup, viscosity rules. Now let's solve a mystery. What happens to the equation in a state of hydrostatics? Imagine a sea where nothing moves. In hydrostatics, velocity is zero. This means the fluid isn't moving and isn't changing. If v is zero, then the viscous term, which depends on movement, also vanishes. We are left with a balance between pressure and gravity. The deeper you dive, the more the pressure crushes you. If gravity acts only downwards, we get the final vector form for hydrostatics. What if we are in an irrotational region? Imagine a whirlpool where the element orbits but doesn't spin itself. For irrotational flow, viscous terms drop out. The Navier Stokes equation simplifies into the Euler equation. This allows us to derive the Bernoulli equation. It's a trade-off. If speed increases, pressure must drop. Solving these for the whole ocean is hard because they are coupled. Pressure depends on velocity, and velocity depends on pressure. Like the Grand Line, fluid mechanics is vast. But with Navier Stokes as your guide, you can predict the path of any current.